Okay, we just had our first lesson in improper integrals. We have two more to go as I think about it. I want to continue on with more examples of functions where the integral is improper because instead of being on a bounded interval, we let x go off to infinity and have an unbounded interval where the function is defined. And that'll be this lesson. And then the following one will be improper integrals for the other reason, namely where they go up infinitely high or go down infinitely low and are not bounded. And so that's another whole class of functions where we have to play with them and figure out how to evaluate them. So let's do a bunch more. And as I say, these are all super interesting, I think. Because you can develop an intuition on them. You learn how to do them, but you also develop an intuition and you really come to understand them. Let's start with this one. Okay. Now, the first thing I want to have you note is that if you were to graph this function, it would look something like this. It's called the Cauchy distribution, actually, probability theory. It's called the Cauchy distribution. But anyway, my question is, can you tell me without even evaluating it whether or not this is going to be something that diverges to infinity as we go from 0 to infinity, or will it converge to a finite number? And the answer is that it's going to converge to a finite number. And the reason is because 1 over x squared plus 1 is always going to be less than or equal to 1 over x squared on the interval, in particular on the interval from, say, 1 to infinity. So this is always less than or equal to this on the interval from 1 to infinity, and we already showed in the last lesson that 1 over x squared, that the area underneath that is finite. And so since the area underneath that is finite, the area underneath this one had better also be finite. Okay, so those are the kinds of things that you need to keep in mind as we go through problems together. So let's do this one, and I'm going to first of all show you kind of a lazy way to just save a few steps. We could start off by writing this as equal to the limit as b goes to infinity of the integral from 0 to b of 1 over x squared plus 1 dx. And then we evaluate this and say it's the limit as b goes to infinity. And now you need the antiderivative of that. The antiderivative of this, recall, is the arctan of x evaluated from 0 to b, and then you go the limit as b goes to infinity of the arctan of b minus the arctan of 0. The arctan of 0 is just 0. And then you ask, what is the arctangent of b as b goes to infinity? And there you have to know what the arctan function looks like. The inverse tangent looks like that. And as you go off to infinity, it approaches pi over 2. So this answer would be pi over 2. So that's our answer, okay? So this is the precise way to do it. This is the way I always do the first few problems, just to make sure that people understand what's going on. But after you've done a few of these, you start realizing, heck, I can kind of mentally do that in my mind and just go ahead and do this. Just write, oh, this is the arctan of x from 0 to infinity. And the key is when you see this, you don't think of plugging in infinity, okay? It's not a number that you plug in. When you see this, you think to yourself, what's happening to this function as x gets arbitrarily large, as x goes off to infinity? You don't plug it in as a number. You just say, what's the limit of this? So as soon as I see this, I never write, this makes no sense. Arctan of infinity, that makes no more sense than to put a smiley face in there, okay? Infinity is not a real number, not unless you get into 1-point and 2-point compactifications in a graduate level topology class. Okay, for us, we say, oh no, that's just going off to infinity, and so we can do that in our mind, and we say, oh, what happens as x goes off to infinity? The arctan of x, as it becomes larger and larger, the arctangent of x approaches pi over 2. Minus 0 is pi over 2. So it just saves some of that work. You just understand that that's what you're doing. Okay, so that's the way I'll do them from now on, just because it makes things easier. So there's that one. Now, what if instead of this we had from minus infinity to infinity? Okay, now we have this situation. As I say, there's 1 over x squared plus 1, and now we're going from minus infinity to infinity. So the easiest way to do that, I guess, is just to use symmetry the way we've done in the past and say, oh, this is just equal, this is equal to 2 times the integral from 0 to infinity, which then would be equal to pi. You could do it like that, or if you wanted to, you could go ahead and just do it straight away and say, oh, this is equal to arctan of x from minus infinity to infinity, and then here's the arctan right there, and say, oh, what happens to the arctan as x goes off to infinity? You approach pi over 2. What happens to the arctan of x as x goes to minus infinity? It approaches minus pi over 2. Those things, and you get pi. Okay, so there you go. I have a bumper sticker on my car. It's been there for about 8 years. And the bumper sticker says, if you can solve this problem right there, you are driving too close. Okay? If you can solve this problem, you're driving too close. I've never had in 10 or 12 years, it's been longer than that, it's been probably closer to, you know what, 2008. So it's been 13 years. It's been 13 years on my car, and I've never had anyone drive past or come up and say the answer is pi. It might be because no one's driving too close. I'm more likely that people don't know how to perform improper integrals like this. Okay, anyway, that's a nice problem. Okay, let's do some more. How about this one? E to the negative x dx from 0 to infinity. Okay, with all these you should have a sense of what the function looks like. Okay, it looks like this. Okay, there's e to the negative x from 0 to infinity. Okay, so there's always 2 questions to ask. One is, does it converge to a finite number or does it diverge? And then the second one is, if it does converge to a finite number, what is that number? Sometimes all you can ever answer is the first one, and sometimes that's enough just to know whether it converges or diverges. Sometimes that's all you need. And I'm talking about real life problems too. If you're talking about real life problems, sometimes all they want to know is this thing going to blow up? Is this nuclear reactor going to stay contained, or are there situations where it's gonna blow up, or where the space shuttle is gonna go wobbling off crazy or whatever else? Okay, so let's think about this one. E to the negative x is the same as 1 over e to the x. And remember what I had on the board in the last lesson? E to the x grows much faster. It grows much faster than any power of x, in particular, faster than x squared. So since e to the x is bigger than x squared, 1 over this is going to be less than this. And we know that this function here, from 1 to infinity anyway, this function here converges. And so we would expect this one to converge. Okay, so again, these are the kinds of things you should be thinking about as we go. By the way, why do we know that e to the x grows faster than any power of x? A lot of these were done with L'Hopital's rule. Let's go ahead and just remind ourselves of that. Here it is right here. What happens to that is x gets large. You have infinity over infinity. This is something from Calc 1, as I recall. Yeah, Calc 1. And so you can use L'Hopital's rule, and it becomes the limit of 2x over e to the x. Take the derivative of each one of those separately, and you still have infinity over infinity. So you can use L'Hopital's rule again, and you're going to get 2 over e to the x, and that goes to 0. So, so the point is this limit goes to 0, which means this thing is overpowering this. Okay? And it took using L'Hopital's rule twice to do this one. If you'd had 200 here, you could use L'Hopital's rule 200 times and you would have gotten the same answer. You would have had 200 factorial here, I think. But either way, the point is this is going off to infinity. That's a finite number, so the limit is 0. So that's why e to the x grows faster than any power of x right there. Okay, so very important. So we know that this thing is going to converge. Before we even begin, let's go ahead and find out what it converges to. And that's easy enough to do. The antiderivative is going to be minus e to the negative x from 0 to infinity. I use the phrase stick in infinity, but that's not what I mean. What I mean is you take the limit of this as x goes to infinity. As x goes to infinity, e to a large negative number is going to go to 0, so that's going to be 0. Subtract. Now you're going to get a negative, stick in a 0, and you get a 1 there. So it goes to 1. Okay, so that thing goes to 1. Okay, let's do another interesting problem. There's all sorts of super neat problems here. This is one of my very favorites right here. This is one of my favorites. X to the n, e to the negative x, dx from 0 to infinity. Okay, is that going to converge or diverge? Okay, now think about it again. X to the n up in the numerator, you would normally think, holy smokes, if you have x to the n, that's a function that's getting big super fast. Not only is the area under that going to infinity, but the function x to the n itself is going to infinity. So certainly the area underneath it, as you go off like this, it just seems to be accumulating like crazy. So that's what you have there, but then you're multiplying it by e to the negative x, right? So you can think of it like this. This thing just dominates that, as we just saw, right? You give me any fixed n, no matter how big that is, 200 or 2,000 or whatever, this thing just washes it away. This thing doesn't hold a candle to this. So this is going to get big much, much faster than this. It sucks it down to 0, and so this thing is going to converge, okay? It's going to converge because and it's not just that this thing goes to 0, but it goes to 0 fast enough, okay? Just, again, to be clear, 1 over square root of x. That thing goes to 0. It goes to 0, but it doesn't go to 0 fast enough, right? The area underneath it is still an infinite amount of area underneath it. But this grows faster than not only x to the n, but it grows faster than x to the n plus 50. So this is effectively much, much, much bigger than this, and so it is going to go to 0 fast enough. Okay? So anyway, let's figure out what it converges to. And I'm going to refer you back to what we did back when we did integration by parts. When we did integration by parts, we did this problem right here and showed that it was equal to, doggone it. Well, I can't remember it. I'm going to have to do it again. Let's just go ahead and do it. So I'm going to let u be equal to x to the n, dv be equal to e to the negative x dx, du is going to be n x to the n minus 1 dx, okay? V is equal to minus e to the negative x, okay? So what's integration by parts say? You take uv u times v, yeah, that's right, u times v, so it's going to be minus x to the n, e to the negative x, minus the integral of v du. So here's v and here's du, so it's minus, there's another negative, so it's going to be plus, doggone it, I didn't give myself enough room here, v du, so it's going to be n, I can bring that out front, x to the n minus 1 e to the x dx. Okay, there it is right there. So there it is. And I'm going to get rid of this now, just to give myself a little more space. So, yep, you can still see that. Looks like that's still visible. And now we're going to go from 0 to infinity. So that means this goes from 0 to infinity, and it also means this goes from 0 to infinity. Okay? So what happens here? We just showed that if you have, it doesn't matter that negative, x to the n over e to the x, which is what this is, and you take the limit of that as x goes to infinity, we just using L'Hopital's rule that that's eventually going to go to 0, right? You use L'Hopital's rule n times, and this thing is going to eventually become just n factorial, and I'll just go use L'Hopital's rule. Dot, dot, dot is going to be the limit of n factorial over e to the x, which goes to 0 as x goes to infinity. Okay, so that goes to 0. What happens when you stick in 0 for x? Then you get 0. So this side, you get 0 on both of these things, and so you end up with just this. Come on. Should have had a negative there. Okay, getting just a little bit sloppy here. Let me be a little more careful. Okay, so those things both go to 0, and you just get this. Well, now, that's all fine and dandy, but notice we have this, but we can use the same result again. Look. What's this equal to? What's this thing equal to? We just have the formula that this thing right here is equal to this. This part goes away, and I just wrote that twice. Okay, yeah, this part goes away, and I just get this. So what's this equal to? What does this formula say? This formula says if I have x to some power times e to the negative x dx from 0 to infinity, all I do is I bring this power out and I reduce it by 1. So that also holds true for this. I can bring this power out, n minus 1, and I reduce it by 1, x to the n minus 2 e to the negative x dx from 0 to infinity. What about this one? I can bring this power out, and I'll be left with this thing like so. And I can keep doing it all the way until I'm left with just this. And this, we just showed a few minutes ago, was equal to 1. So this is just equal to n factorial. How cool is that? So this integral here, this is for when n is a positive number. I could just say a natural number. It's a natural number or a positive integer. Okay? It's just going to be n factorial. How cool is that? A really neat result. Okay? Really neat result. Okay, very good. Well, there's some other ones that we did. Remember, we did this one, e to the negative x sine of x dx. We just found the antiderivative of that. Doggone it, I can't remember exactly what it is now, but it was e to the negative x over 2, I think. And don't quote me on this, but it was a sine of x in here minus cosine of x, or else it was cosine minus sine, something like that. Something like that. I guess it's going to make a difference, and I can't remember which one it is right off the bat. The point is, I'll let you go back and check it out. The point is, if you evaluate this thing from 0 to infinity, boom, you're going to get the result. You're going to get the result. So I'll leave that as an exercise for you. Go back and find what the antiderivative of this thing was, and then evaluate it at the endpoints. And the endpoint meaning you let x go off to infinity there. Okay, which of course will go to 0. But when you stick in a 0 here, I bet, you know what? I bet it was cosine minus sine. I bet. No, I bet it was sine minus cosine. Because if you let x go to infinity, you're going to get e, as this thing goes to infinity, it's going to be 0. Now you subtract, and now you put a 0 in there. What are you going to get? E to the 0 is 1, so it's going to be 1/2 there. The sine of 0 is 0, and the cosine of 0 is going to be 1, so it's going to be a minus let's see. When you stick in infinity, that's going to be infinity. When x is 0, you're going to get e to the 0, which is 1/2. That's why that was there. Times the sine of 0 is 0, and then the cosine of 0 is 1. So you're going to get that. And so that gives you positive 1/2. So that looks right. Make sure that my computer is still working. Okay, good. So there's that one. Okay. There's that one. Let's do another one. This is kind of a cool one. Okay, again, you should notice that this thing here is going to be less than 1 over x squared. So since 1 over x squared gets small fast enough to converge, this one should also get small fast enough to converge. The one thing we have to worry about here is that this thing right here is going to have some vertical asymptotes as well. Right? This is x plus 2 times x plus 4. Agreed? So this thing is going to blow up at -2 and -4, but that doesn't matter. We're starting at 0, so at 0, it's still basically just going to be decreasing like this. It's going to blow up maybe there, and maybe something like this, and maybe something like this, whatever. But at from 0 on, it's going to be basically a function which lies underneath 1 over x squared. And we know that the area underneath this thing is finite, so the area underneath this thing is going to be finite. Okay, anyway, I brought this one out because it reminds you of, hopefully, how do you solve a problem like this? Here you're going to need to use partial fractions again, right? Let's go ahead and do it. Good practice in partial fractions. So the first thing we need to do is to take this and write it as 1 over x plus 2 times x plus 4 is equal to a over x plus 2 plus b over x plus 4. And then you get 1 is equal to a times x plus 4 plus b times x plus 2. And then you stick in a couple of judicious values for x. Let's let x be equal to -2. If x is equal to -2, then you're going to get what? 1 is equal to, that's going to go away, you're going to get 2a here. So that tells you that a is equal to 1/2. If you let x be equal to -4, then you're going to get 1 here. This thing goes to 0. You're going to get -4 plus 2 is going to be a -2b. So that tells you that b is equal to -1/2. See that? So a is equal to 1/2. B is equal to -1/2. So let's just let me get rid of this for a moment, and let's just look at. In fact, I'm going to get rid of this for a moment and just look at this right here and say what's the antiderivative? It's going to be, I can factor the 1/2 out front. The 1/2 comes out front. I have 1 over x plus 2 minus 1 over x plus 4 dx, and that's going to be 1/2 the ln of x plus 2 minus ln of x plus 4 right there. Okay, there's the antiderivative. So now I can get rid of all this stuff, and so now that's plus c if you want to. There you have it right there, and this is 1/2 of the whole quantity there. Okay, so now I can go back to the definite integral or improper integral here. So this thing right here is equal to 1/2 the ln of x plus 2 minus the ln of x plus 4, all from where? I think this went from 0 to infinity. Okay, from 0 to infinity. Dang, how do you handle this thing? As x goes to infinity, this thing is going to go to infinity, this thing's going to go to infinity, so you have something of the form infinity minus infinity. That's one of those indeterminate forms, okay? It could be any answer. You could have 2x plus 7 minus 2x. That's going to go to 7. If you had a 17 here, it's going to go to 17. It can go to anything you want. If you make it 3x, it's going to go off to infinity. So it could do anything. If you had just 2x and 2x, it would go to 0. So the answer could go to anything if you have something of the form infinity minus infinity. How do we handle that? What do we do there? Any ideas? Any ideas? This is where, again, you need to know your functions and your functions well enough that you actually see possibilities in your own mind. Here's the possibility that I see. I say, oh, the ln of one thing minus the ln of the other, that's the ln of the first divided by the second. There, that's all we need right there. Because now what happens? As x goes to infinity, this and this ratio here is going to approach 1, okay? That's going to approach 1. You can use L'Hopital's rule on that if you want to, or just divide both the top and the bottom by x, and you're going to see it. It's going to go to 1, and the ln of 1 is equal to 0. So as x goes to infinity, you're going to get a 0 there. Now you subtract 1/2 times the ln of what happens when you put in a 0 here. Put in a 0, you're going to get 2/4, 2 over 4. And so that is equal to 1/2 the ln of 2 as your final answer. Okay, you see how I got that as the final answer? I did it awfully fast. This was 1/2 right there. The ln of 1/2 is the negative of the ln of 2. So the ln of 1/2, I brought the negative out front and canceled with this one. There, that 1/2 stays there, and this is now the ln of 2. So a really nice problem. That's this one right here. Okay, so that's the one we were after. Okay, so I I could do all sorts of other problems for you here. Let me just kind of show you some of them. How about this one? Okay, I want to stay away from 0 because this thing blows up at 0, right? And so on. So we're going to talk about that in the next lesson. But for now, I want functions that don't blow up. They don't have vertical asymptotes. So we'll stay away from 0 here. So what about that? Does that converge or diverge? If it does converge, what does it converge to? Okay. Well, again, if you really understand the rates at which things grow, you'd say instantly that thing converges. Why do I know it converges? Because I know that the ln of x grows slower than any power of x. It grows slower in particular than the square root of x. Okay? It grows slower than that. I know that. Since that's the case, this thing is going to be less than or equal to this thing. Agreed? And that tells me, of course, that this is equal to 1 over x to the 3/2 power. And what do I know happens if you find the area underneath x to the 3/2 power from 5 to infinity? For any power of x bigger than 1, if this thing is bigger than 1 right there, this thing converges. And so since this thing converges right here, and since this function here is always less than or equal to this one, 1 over x to the 3/2 looks something like this. This one's going to be underneath it. The area underneath that also has to be finite. Okay? So those are the things. You have to just be so aware and familiar with these functions that you can just see that you're going to piece it together like this. It's not just a matter of nodding your head when someone shows it to you. It's a matter of being able to have thought about this in the first place. You just look at that and you say, oh, this grows so slow. Boom, you got to have that. Okay? So I'll let you do this one. This is a nice problem. Back when I was a graduate student at Iowa State University, I had so much fun teaching my courses as a graduate student. I actually volunteered to make up the whole departmental final and midterm, and this was one of the problems I put on the final, was that one right there. And a lot of students had problems with it. Okay, I'll get you started on it. Remember integration by parts? You use integration by parts whenever, not whenever, but quite often when you have the product of functions that are different from each other. So here you have a logarithm function, and you also have an algebraic function. Okay, so I'll let you du is equal to 1 over x dx, and I'll let you take it from there. Okay, so you go ahead and find out what that thing converges to. Okay, what about this function? Let's change it just slightly. What about that? Does that converge or diverge? Again, you should be able to look at that just instantly and say, oh, that diverges. Why? Because we know that 1 over x diverges. This thing doesn't go to 0 fast enough. It goes to 0, but not fast enough. So the area underneath that is infinite. And this thing, ln of x, is ln of x over x is bigger than 1 over x. Okay, as soon as you pass e, it is, whoops, the other way around. This one's bigger, okay? So the point is, since the area underneath this thing is infinite, this thing is going to be above it. So the area underneath that thing is infinite. So there you can do it. This one is easier to do. All you have to do here is just use a regular substitution. Let u be equal to the ln of x. du is equal to 1 over x dx. Look at here. It's going to be u. 1 over x dx is just du. You can actually go through this process if you want and say, well, let's see now what happens as when x is equal to 5. This is going to be the ln of 5. You can do that. And then you say, what happens as x goes to infinity? As x goes to infinity, the ln of x is going to go to infinity. So that's fine to do that, okay? Just have to be careful as you do it. And now, what's the antiderivative here? It's going to be 1/2 u squared from ln of 5 to infinity. And what happens to u squared as u goes to infinity? Obviously, that goes off to infinity, okay? So you got things like that. Okay, let's see if there's any others I want to do here. Here are some other ones. Okay, does that look familiar? That's the kind of function we could have used the arctangent substitution for, right? Let x be equal to arctan of u. And if you want to, you can go through that whole process. But what if you just want to determine whether it converges or diverges? Can you tell? I can tell because I say to myself, look, this thing here, by the time you take the square root of x squared, you effectively have an x there. So this is an x, that's an x, x times x is x squared. As long as you have something here in the denominator that's greater than 1, it's going to converge. So boom, I know that's going to converge. I guess another way of doing it is just saying that this thing right here is always going to be slightly less than this, right? Because if you didn't have the 1 there, they'd be equal. With the 1 there, this is slightly less than that. And so since this thing converges from 5 to infinity, so will this one. Okay? What if I had an x upstairs as well? Or say an x plus 1 upstairs. Then I'd say, well, okay, now effectively, how big is this thing growing? This is the same size as this, so they kind of cancel out, and I end up with roughly just effectively a 1 over x there altogether. And I say, oh, what do I know about that? That thing diverges as you go from 5 to infinity. So that one would diverge. So we're going to get into this a whole lot more when we get to sequences and series, but I just kind of want to get you kind of thinking about it now, because it's the very same idea. Okay? Any others I want to do? That's probably good. That's probably good for the present. Okay? So that's the idea. So so in the next lesson, we will look at functions that blow up like this. Okay? They're also good. They're not quite as interesting as these, I don't think, because these connect to sequences and series as well. But anyway, still good. Come on back.